Welcome everybody. We are in the central laboratory of Semmelweis University, and I would like to show you in this video how the samples are handled, how the measurements are done, so you can have a brief understanding of the work we do here. Because of the coronavirus, we took some extra safety precautions since the samples were previously taken to an inner part of the lab, but now entering through the front door here is prohibited, and we ask everybody to put the samples in these trays through the small window. These samples are brought here from all clinics of the Centrifugation University and also from other parts of the city and even the whole country. On a normal day we process about 3,500 tubes from about 2,000 individual patients. Once the samples have arrived, we need to sort them, prioritize them and get them ready for the measurements. These steps are usually done with automation, but there are a few samples that need to be taken care of manually. Besides bringing the samples by foot, we also have a tube system in the building. All floors and departments are connected to the laboratory, so this is a fast and safe way to send us samples. The tubes are placed in capsules to avoid any damage to them during the transfer. The capsules are then emptied and sent back to the original department. These capsules are labeled so the departments don't use each other's, and since everybody has extra capsules, the transferring of the samples to the laboratory is continuous, so they don't have to wait for us to send the capsules back immediately, although we try to do it obviously. We have different kind of tubes that we use in the laboratory for the measurements. They are color coded and the colors represent the additives that are inside the tube. The most commonly used are these red types that have a clot activator inside them. And some of them are also filled with a gel that will help separate the cells from the serum after centrifugation. The clot activator will make the clot form faster because we need to wait with the measurements until all fibrinogen has been transformed to fibrin. The white cap tubes have no additives inside. We use them for the urine and the spinal fluid measurements. The other tubes have all anticoagulants filled. The blue types, for example, use citrate for anticoagulation. Now the citrate is the only additive that is in a liquid form. All others, like the clot activator, are lyophilized, so they are not going to dilute the sample. The citrate, however, will, as you can see, it's in a liquid form, so it is very important that the right amount of blood is drawn into these kind of tubes. Now normally when you are drawing the blood you don't have to worry about this because they are vacuum sealed, so the amount of air evacuated will determine how much blood the tubes are going to be filled with. Unfortunately the vacuum can escape, so you will need to see if it's filled correctly. Now the level of the blood is indicated with a mark on the side of the tube, as you can see here. And as I said, since the citrate is a liquid, it is very important to fill the tube with the desired amount of blood. So the dilution factor will remain constant and that the machines will give us the correct results. If the other tubes have less blood or are overfilled, we will still be able to use them, but with the citrate, as you can see, it's a different mark. It's an arrow because it's very important that the right amount of sample is inside. We also have a long tube used for the sedimentation rate that also uses citrate. The other anticoagulant is EDTA that these other tubes have inside them. The purple is used mainly for the blood count and the blood group measurements, while the gray ones with also EDTA, they have fluoride as well that will stop the glycolysis. Since the red blood cells use the glucose to produce energy, after a few hours we would have false results. So if you want precise glucose levels, we need to use these gray tubes for the glucose measurements. With all tubes that contain anticoagulants, it is important to note that once it is filled with the right amount of blood, you need to mix it carefully. Don't shake it, just tilt it a few times. If you put it down on the table before doing so and fill the next tube, you can have clots forming very fast, and those microclots can interfere with the measurements. In hemostasis, the pre-analytics is responsible for approximately 60% of the errors, either because the blood volume is incorrect or the clot formed inside the tube or the blood hemolyzed, etc. So it is important to take the blood draw seriously. Here we see a few examples of blood after centrifugation. The gel seen in the middle separate the cells from the serum. The first one is a normal sample. The serum is transparent and has a straw yellow color, mainly because of the proteins inside. On the bottom you will see the red blood cells and the white blood cells just below the gel. The next sample is cloudy and slightly whiter in color. It's called lipemia, which is caused by the high amounts of lipids in the blood. This is one of the reasons why blood testing requires previous fasting, because the lipids can interfere with our measurements, especially in hemostasis, but of course we will measure false high amounts of lipids, because this can be seen not long after eating. One of the most common errors that can occur is the hemolysis of the red blood cells. If they are damaged, they will release the hemoglobin from inside, which will color the serum bright red. This will also interfere with the measurements in a number of ways. If the spectrophotometer uses this red spectrum to measure, then we will have false results. Or, as the red blood cells also release enzymes and ions from their cytoplasm, those will also be added to the serum, giving us false results. The last sample type is the Ectric Serum. This is a dark yellow or brownish in color. It's caused by the high amounts of bilirubin. So the three are hemolysis, lipemia and icterus. Some of these are caused by a disease, so it cannot be altered like the high bilirubin, but hemolysis with this bright red color usually happens outside the body. So that means that the blood was mishandled in some way. They either used a small needle to draw the blood, or this also happened a lot of times using the cannula, or the sample was placed in a high or low temperature, or it was dropped on the floor, it was shaken. So in these cases the red blood cells can be damaged and the hemolysis will occur. A csövet erősen, ezért is hemolizálhat, tehát erre is nagyon fontos odafigyelni, hogy a mintákat óvatosan bánjunk, mert ezek sajnos a mérést fogják nekünk megnehezíteni, és adott esetben nem fogunk tudni belőle eredményt kiadni. After receiving the samples, first we put them into the tube processing machine that will scan the barcode and sort out the samples according to what needs to be done with them. For this we have specific trays that handle all types of tubes, even the small ones, the big ones, it doesn't matter, we can process them. Here we have tubes that have already been centrifuged, others have just arrived to the laboratory, but we can mix them as well in the trays, since the machine will know from the barcode where it needs to be sorted out. The barcode reader is inside the arm that picks up the sample, so it knows which patient the sample belongs to, whether it needs centrifugation or not, and what measurements need to be performed on which analyzers. Most analyzers can puncture through the cap, so that needs to be taken off after centrifugation, which is also done automatically by the sorter. Here you can see the decapper in progress. It is a useful function because taking off the caps from thousands of samples every day can be a hassle. Once all measurements are finished, the samples are brought back here, where the tubes will be closed with a plastic cover to stop the evaporation, and the samples are then archived, meaning they are stored in a numbered rack, so we can track exactly where the samples are located in case we need them for further measurements. Another useful function is the aliquoting feature. What this does is that it scans the original sample, and if needed it will make a secondary tube with the same barcode and pipettes some serum into the other tube. This way we can start measuring on two different machines at the same time. It makes the measurements run faster since we don't have to wait for the first analyzer to finish processing the original sample, and we can start it at the same time. The samples that are ready for measurements are sorted into these trays that are labeled for us to know which analyzer it belongs to. So every rack, every position has its distinctive purpose that's programmed in the sorter. So with this system the laboratory staff will know which samples they need to take to their analyzer. Here we can see the aliquoter in progress. The same barcode will be printed on the secondary tube and placed behind the original sample. This can be done with multiple secondary tubes depending on how many are needed. The sorter will take the pipette tip and take a specific amount of sample out of the original tube and fill the secondary tube with it. Moving on to the analyzers. This lab is a semi-automated lab because although the sorting and the analyzing is done in full automation, the sample needs to be carried from one machine to the other manually. So for example, from the sorter to the analyzer, we have to bring it here. For the measurements, we need to put the sample into racks that are specific to the analyzers, so they are not interchangeable. The barcode needs to be facing the reader, this direction. And after we put the racks with the samples inside, we just need to start the analyzer and it will perform the tests automatically. Everything is linked online to the laboratory system, so almost all analyzers know from the barcode which patient it belongs to and what tests need to be performed. The analyzers use different methods to analyze the sample. This clinical chemistry machine is the most essential analyzer in the laboratory, as it measures the most common parameters in the daily use, from glucose to ions and proteins, lipids, enzymes, etc. It uses three methods to measure. The first is a potentiometry to measure the concentration of ions using ion selective electrodes. We use it for the sodium, for the potassium and the chloride. Then it uses spectrophotometry for most of the tests, like the glucose, the lipids, the metabolites and the enzymes. Then with turbidimetry, it measures the more complex proteins like the CRP, the ferritin and the microalbumin. With spectrophotometry and turbidimetry, the analyzer uses reagents to perform the tests. These reagents are ready-to-use liquids. They are labeled with a barcode, so the analyzer can track the lot number, the expiry date and the remaining tests that can be performed. We only need to put the reagents into the cooled reagent holder, and with the barcode it will automatically recognize the reagent and use it for the measurements.
Akkor ezt ő követni tudja, ezzel nekünk nem kell foglalkoznunk. Ezeket a reagenseket a megfelelő tartókban elhelyezve.
These are the two reagent holders that are loaded and the analyzer will take it from here and mix it with the sample.
És ebből fogja a mintákat, vagy a mintát ezzel fogja összekeverni.
Here we can see an overview of the analyzer with the previously mentioned reagent holders and the incubation chamber in the middle, where the reagents are going to be mixed with the patient's sample in cuvettes and then incubated in 37 degrees Celsius until a specific time that the method requires.
És utána 37 fokon inkubáció után, ha spektrofotometriáról van szó, akkor a hullámhossz alapján olvasok, illetve a turbidimetrián is esetében is a végén megkapjuk az eredményt.
So we just put the sample in the rack with the barcode facing the reader and start the analyzer. Once the barcode is scanned, the analyzer will download all the necessary information from the laboratory system, like patient data and the tests that require to be measured. It will start the test, and once the incubation is over, the light scatter or the intensity of the light will be measured, and the result will be calculated and sent back to the laboratory system.
Most olvassa be a mintákat, és utána meg is jeleníti nekünk nem sokkal később, hogy kihez tartozik, milyen vizsgálatot kell belőle végezni. Maga a mérésnek az ideje is változó, az ion-szelektív elektródáknál nagyon gyorsan.
The time it takes to measure the sample depends on the test it is performing. The potentiometry to measure ions takes only a few seconds, but where reagents are used, it takes anywhere from 7 to 20 minutes depending on the complexity of the method.
A készülék nem cseréli a tűt, tehát egy darab tűt használ, amit majd folyamatosan nyilván elfog.
The analyzer first takes some sample out for the 3 ions to measure with potentiometry. The needle used for this is going to be washed off for each patient, so it will not mix the samples. After that, the rack with the tubes are transported to the back of the analyzer, to these arms, and they are going to take out the serum for the remaining test and transfer it to the cuvettes located in the middle. The arms above the reagent holder are going to take the reagents and fill the cuvettes with the patient sample. These needles are also in constant cleaning to make sure that there is no cross-contamination. Because of this, the analyzer uses a lot of water and a cleaning fluid. The water is purified 2 times to make sure it doesn't contain any contamination, like ions, because that will interfere with our results. The analyzer has its own water purification system where the ions are extracted to have the purest water possible. The arms with the green needles are used to mix the sample and the reagents in the cuvettes. Once the reaction is over and the results are calculated, the cuvettes are going to be reused, so it is important to clean it properly to make sure no contamination occurs. These brown tips are used to clean the cuvettes. After a while, the cuvettes from the constant use are going to be damaged. They will become blurry, so the analyzer measures the amount of light that can pass through the cuvettes, and once it exceeds a limit, it will not use it anymore to measure. Those are then going to be replaced with new ones. Here you can see how the arm reach into the reagents and then transfer them to the cuvette. The cuvette holder and the reagent holders are constantly turned to move the required reagents or the cuvette below the needles, since the needles cannot move. As you can see, once it takes out the reagent, it fills the cuvettes and immediately washes the needle with water and washing fluid to prevent the contamination. Before any measurements can be performed, we need to make sure that the analyzer is working properly. To do that, we need to measure controls. This is the most important task in the laboratory practice. We get controls from 2 sources. The manufacturers of the analyzers provide us with the internal controls which are used every day, and we can get external controls from other companies that specialize in laboratory testing. We measure the external controls 2 to 6 times a year depending on the test. The controls are basically stabilized samples with known results. The results of the controls are stored and can be viewed for future reference. We can look at them for 1 day, or we can view a wider period of time to see how it changes from time to time. The controls are measured in 2 different concentrations to make sure that the reference and the abnormal range are both covered. This way we can make sure that all patients' results are going to be correct. There is a mean value of the controls, and the results that we just received are compared to that, so on the Lewis-Jennings graph the standard deviation is going to be shown. Some difference are allowed. We usually try to keep it below the 1 SD value. If the values are in that range, then the analyzer is ready to use, otherwise we need to calibrate it. Here you can see a few examples of the controls from today. They are all around the mean value. If we are not pleased with the results, we need to calibrate it, which means that the curve that the analyzer uses to calculate the results need to be changed. This is the calibration curve. It uses either 2 points or multiple points to draw the curve and to calculate the results. We can view the controls from just today, but it is also informative to go back for several days and see how the controls changed over time. Here we see the Lewis-Jennings graph from the glucose in the last month. The 2 colors represent the 2 different concentrations. This is how it should look like. All results are around the mean value, so the analyzer is working properly. To determine whether the machine needs any maintenance, we can analyze these graphs, and using the Westgard rules, we can detect any errors that need intervention. For example, if the results are always below the mean value, that is an indication of a systemic error, even if the values are close to the mean. So it's important to look at the results not just for the day, but for many previously. Besides measuring daily controls, it's important to perform the scheduled maintenance for the analyzers. There are tasks that need to be performed on a daily basis, while others are only once a week, once a month, or even just once or twice a year. The latter are performed by the technicians from the company, but the daily, the weekly and the monthly maintenance are done by the laboratory staff. This includes the cleaning of the pipettes, the tubes, or the replacing of the unused cuvettes, for example. As you can see, we have two analyzers that are identical. They are more or less measuring the same parameters. This is important because we try to separate the urgent samples from the routine ones to make sure that we can give out the results as fast as possible. We have 1 hour for the urgent samples. That includes the sorting, the centrifugation, the measurements and the technical validation of the result. While for the routine samples we have 4 hours to do all that. So we measure the urgent samples on the first analyzer while the other is used for the routine samples.
A rutin mintákat pedig a másikon. Egy másik lehetőség még, amivel el tudjuk különíteni a mintákat, az, hogy vannak különböző színű rekkeink.
Another way to distinguish between the urgent and the routine samples are by using different colored racks. These are recognized by the analyzers, so it will take the red urgent racks in front of the gray ones. This way, if there is a queue, then the urgent samples will be performed first. The number of cuvettes are limited, so if all of them are in use, then all the samples have to wait for the previous ones to be finished. But the main system to separate the urgent and the routine samples are by only using the one analyzer for the one sample type. In night shift, we only have the urgent samples, so only one analyzer is performing the tests. It's also useful to have two identical analyzers, because in case one breaks down, we have a backup, so we can perform the test 24/7. And also, while the controls are being measured or the scheduled maintenance is being performed, we cannot use the machine for the patient samples, so to make sure that we don't stop for a second, the other analyzer can do all the work in that time. So we usually do the maintenance and the measure of the controls in the morning on the routine analyzer, and do this at noon on the urgent analyzer. This way we can have a continuous workflow all day and all year.
Tehát folyamatos lehet a mintamérés, tehát normál esetben nincsen leállás egyáltalán sem.
Let's move on to the hormone, the tumor marker and the drug testing. Compared to the clinical chemistry, here we measure more complex molecules, so the method needs to change as well. The previously described immune turbidimetry cannot be used here because we have a much larger analyte to detect. The tests used here are immunoassays, which rely on an antibody-antigen reaction, where at the end of the reaction you can detect either a radiation, a color change or the fluorescent light. The method used varies by companies. In this case we have a chemiluminescent microparticle immunoassay.
Viszont mivel összetettebb molekulákról van szó, nem lehet egy sima egyszerű turbidimetriával vagy egy egyszerű kémiai reakcióval meghatározni a mintából az eredményt, tehát már egy összetettebb folyamatra van szükségünk. Maga az felépítése a készülékeknek nagyon hasonló, itt is rekkek vannak.
The main concept for everyday users are more or less the same as in a clinical chemistry analyzer, so we have racks to put the samples in. Once the barcodes are scanned, they get the information from the laboratory system, and just like previously, the measurements are performed automatically. The cuvettes used here are not washable, so they are only going to be used once. The reagents are mixed with a sample in these cuvettes, and after the incubation time and a few washing steps, the relative light unit can be measured, which is going to be proportionate to the concentration of the analyte. The results will be sent to the lab system for technical validation. These analyzers also have tests that need to be measured 24/7, so we have to have a backup machine here as well. The measuring of the controls are also the most important task here, because otherwise we wouldn't be able to tell if the results we give out are good to use. Just like on the other machines, besides the maintenance, we have to measure the controls every day. In immunoassay, the measuring range is a bit wider, so we usually have 3 control concentrations. We have a low, a medium and a high one. If the controls are in the range, then we can start working, otherwise we need to calibrate the analyzer. Since the analytes and the methods are more complex compared to the clinical chemistry, the calibration curve is a bit different too. It uses more measuring points to determine the concentration of the analyte.
készülékben, hogyha egy lotszámváltás történt, akkor is természetesen lehetnek eltérések, ezt nekünk kell folyamatosan figyelnünk, és hogyha minden megfelelő, és a kontrollok megfelelőek, akkor elkezdhetjük a napi munkát. Hogyha a kontrollok kilógnak a sorból, nem megfelelőek, akkor kell megint csak kalibrációt végrehajtani. Itt, mivel összetettebb molekulákról van szó, általában azért több pontos kalibráció szokott lenni, legalább 2, de inkább még annál is több, 4 vagy 6 is előfordul. Akkor meg is érkeztünk a hemostázishoz, tehát az alvadás.
Next, we arrive to the hemostasis, where we measure the parameters involved in coagulation. Since we use anticoagulated bloods, I have to highlight again the importance of the pre-analytic phase, because we see a lot of errors every day, because there is either not enough blood in the tube, or it is hemolyzed, or it has a clot inside, etc. The concept of the measurement depends on the analyzer, and there are mainly two major techniques used. To start off with, we have a blood sample mixed with citrate, which is a reversible anticoagulant, so if we start adding calcium and other factors, the blood will start clotting again. During this process, the fibrinogen converts to fibrin and causes a mesh. It's important to note that this is not the whole clotting process, since we would need to wait for the factor 13 to stabilize the fibrin as well. Rather, the analyzers are only going to measure the time it takes for the fibrin mesh to appear after the calcium has been added. The way they detect the mesh is what differs between the two major techniques.
Ez fontos hangsúlyozni, hogy itt nem a pontos alvadást fogja nézni, tehát igazából a végső alvadás az lenne, amikor már a 13-as faktor is keresztkötötte a fibrinogént, vagy a fibrint, de itt alapvetően a készülékek azt fogják nézni, hogy ahogy megjelent ez a fibrin háló. Ez egy nagyon-nagyon fontos dolog kihangsúlyozni, mert a készülékek különböző elveken működnek.
This analyzer, for example, uses an optical detection method to measure the amount of light scattered from the sample. As the fibrin mesh appears, the light scatter changes and the time in seconds can be recorded. The other technique involves mechanical detection, where a small metal ball is moved with a magnet, and as the mesh forms, the viscosity of the sample changes, and therefore the metal ball is going to be stuck after a while. This can be detected by the analyzer, and again the results are given in seconds. Normally, the two techniques should give the same results, but unfortunately the seconds measured can be very different based on not just the technique, but also the manufacturer's reagents.
Tehát nagyon fontos, hogy ugye ezért vezetik be az INR-t, hogy valamennyire a készülékek összehasonlíthatóak legyenek, ne csak a szekundumot nézzük, hanem legyen egy standardizált érték, amivel meg fogjuk tudni mondani, hogy mondjuk a protrombinnak milyen a szintje. Na most ettől függetlenül természetesen az INR sem tökéletes, azért vannak különböző eltérések.
To standardize the results, the International Normalized Ratio, or I/R, was introduced, and therefore the results can be somewhat compared to each other. On the lab report, we show the IR and the seconds as well, which can also be informative in some cases, but the different lab results should not be compared using the seconds, only the I/R. The measuring process is the same as we have seen before. The samples are put in a rack, and the barcode is scanned, the measuring starts.
Azonosítja a mintákat, és elkezdi majd a mérést belőle. A protrombin idő mellett még egyéb alvadási paramétereket is meghatározunk, apti, trombin idő.
Besides the INR, we measure the thrombin time and the APTT a lot on these analyzers. The concept is the same, but different additives are used to differentiate between them. Just like with the prothrombin time, these are also hard to compare between the laboratories. In fact, we ask not to do that. With APTT, what we can do is, if we take the median of the reference range and divide the results with that, then the ratio we get can be compared by the different laboratories. Normally the reference ranges could also help in comparing the results, but that's just a rough estimate, so we ask to try and avoid that. In some instances, like the fibrinogen and the dimer, the reference ranges should be determined according to age, but it is not extensively available yet.
Külföldön már több laboratórium is dolgozik rajta, és használják is. Természetesen a rutin paraméterek esetében, tehát a
Beside the thrombin time, prothrombin time, and APTT, we routinely measure fibrinogen, D-dimer, and we also measure specific hemostatic parameters like factors, protein C, protein S, antithrombin, and a lot more. These are performed on the same analyzer as this one, but with different reagents. We try to separate the routine hemostasis from the specific test because the two would slow each other down, and the amount of reagents that can be used are also limited, so we need to separate the analyzers to do both tasks. If a machine breaks down, we have a backup as well, so in these cases we can move to the specific analyzer and perform the routine test there, or the other way around. We came to the end of the session, so I would like to introduce Balázs Tóth, who will show the urine and the hematology measurements.
Let's go to the Urinalysis Lab. Urinalysis consists of chemical examination using test strips and microscopical examination of the urine. The detection method of test strip analysis is that on the strip there are 10 different pads which contain chemical reagents, and this instrument pipettes the necessary volume from the sample to the pads. And then the color of the pads changes, which is detected by the instrument. The rate of color change depends on the concentration of the analyte. The result is semi-quantitative data shown as crosses. The next instrument is an automated urine microscopy system. The method here is that after a hydrodynamic focusing, urine particles flow in a thin layer, and the digital camera coupled to the microscope captures images of the different particles. An automatic particle recognition software analyzes these images, uses size, shape, contrast, and texture features to classify each image into one of the categories. Here a sample can be seen. The particles have already been classified into red blood cells, white blood cells, bacteria, artifacts, and unclassified particles. The operator must check if the classification by the instrument is correct, and if there are misclassifications, manual classification should be performed. On the screen we can see that these particles have been classified into white blood cells, which is mostly correct, but there are some particles with bad focus, which are difficult to recognize if there are cells or not, so we remove them and accept the rest. Here bacteria can be seen. The instrument was correct, so we move to the next page. These are epithelial cells, which are misclassified in many cases because they have many different shapes and categorized as unidentified particles, so the operator has to classify them as epithelial cells. Here are some epithelial cells too. We put them into the epithelial cells. Here are some bacteria as well, which were not recognized by the instrument. and here some white blood cells were not identified. In the end, we compare the microscope results to the chemical strip results to check differences. Here we can see that they are similar. The test strip detected 2+ white blood cells, which is equal to the results seen during the microscopical examination. Let's see the hematology instruments. First, the hematology analyzer. One of the detection methods is that red blood cells and platelets are passed through a small opening known as aperture, which is surrounded by 2 electrodes. As the blood cells pass through this aperture, the direct current resistance between the 2 electrodes changes proportional to the size of the blood cell. White blood cells are detected with a different method, flow cytometry, so the cells are flowing through a very narrow flow cell and illuminated by lasers. Detectors placed at different angles detect side-scattered light and forward-scattered light. Forward-scattered light is proportional to the size of the cell, side-scattered light to the content of cell. Fluorescence dye is used by the instrument too, which binds to the RNA of the cell, so information about the nucleic acid content is provided as well.
Az oldalirányba szórt fény a sejteknek a granuláltságától, illetve még fluoreszcens festéket is használ a készülék, amellyel a fehérvérsejtnek az RNS-ét jelöli meg. Ez pedig arról ad információt, hogy fehérvérsejtekben mekkora mennyiségben van jelen az adott örökítőanyag.
Instrument screen, the obtained data are displayed numerically and in the form of histograms and dot plots. For example, the dot plot of the white blood cells can be seen here. On the x-axis is the side-scattered light, on the y-axis is the fluorescent light intensity. With these data, the types of white blood cells can be differentiated. Pink dots are the lymphocytes, greens are the monocytes, dark blues are the immature granulites, light blues are the mature granulites, and basophils. Reds are the eosinophilic cells. Under it, it is the red blood cell histogram where the size distribution can be seen. Using this histogram, the instrument can provide data of a parameter called RDW. At the bottom, the platelet size distribution can be seen. In some cases, for example, ITA-induced pseudothrombocytopenia, where the instrument displays false low number of thrombocytes, checking this histogram is very important. When an increase can be seen at the higher ranges, it can mean thrombocyte aggregates. Sometimes it is necessary to make a blood smear from the sample. For example, if the white blood cell count is high, or low platelet count, or high basophilic or eosinophilic cell count, or if the instrument flags the sample suspicious of blood cell or abnormal lymphocytes. In these cases, blood smear is made. The required volume depends on the hematocrit value, usually around 3 to 5 microliter, which is spread and stained on a microscope slide. The gold standard of blood smear examination is manual microscope counting, but here there is possibility to examine the sample with an automatic instrument. The advantage of this that the instrument itself checks at least 100 cells, and classifies them into categories like the Urine Microscopy instrument, and it is also possible to modify each classification.
A különböző fehérvérsejt típusokat. Ezen az képen például azt látható, hogy itt
on the screen we can see neutrophil granulocytes. The automatic classification seems correct.
Vízzeletüledékvizsgálathoz itt is lehetőség van arra, hogy átrakosgatjuk a különböző képeket más kategóriákba, ha úgy ítéljük meg, hogy magának a készüléknek a szoftvere az tévedett. Itt ezen a képen nem látok olyat, ahol esetleg tévedett volna a készülék, ez így nagyjából rendben van.
Here we can see eosinophil granulocytes. Here we can see an image which was classified as basophil granulocyte, but it seems to be an artifact from the staining, so I move it to the artifact category. These cells are lymphocytes. The instrument made a correct classification here. These are monocytes. It is correct as well. It is an atypical lymphocyte. It is a staining artifact too. The instrument misclassified it as a plasma cell. Some more staining artifacts which are misclassified as thrombocyte aggregates, so I move them to the artifact category. And on the last tab we can see the artifacts. The instrument takes a picture of a view field where the morphology of the red blood cells can be evaluated. An automatic evaluation is also done, which can be modified if the operator has different opinion. Here, the automatic evaluation says that there is polychromasia, which in some cases is false, because quality of the staining influences the recognition of it. I can't see polychromasia on this image, so I modify this result manually. Anisocytosis, which means the cells are present in different sizes, and microcytosis are marked by the instrument, which is correct, so no modification is needed. In the end, the result is validated, which means no more changes are possible.